up until now, we focused on nomenclature, haven't we? We've talked about naming alkenes one after another, after another, after another, after another, after another. And we haven't really talked anything else about alkanes. And I told you the template was going to be very similar to alkanes. We talk about the alkane family. We talk about the functional group that makes it an alkene. We talk about naming the alkenes at the very basic fundamental level. And then we go in and we talk a little bit about structure. So that's what I want to do in this video. I want to talk to you about the structures of alkanes and how it's somewhat different than the structure for alkanes. All right, so here is the discussion that we need to have. If you go back and if you review your notes from Lecture 3, Module 3, when we talked about alkanes, we got to a point where we started drawing structures that look like this. All right. Do you remember what we called these? That's right. These were Newman projections, just like the Newman salad dressing. All right, so those Newman projections were drawn. And the reason is because the carbon-carbon bond, any bond actually, if it's a sigma bond, can freely rotate. So what we see is a rotation that can begin to happen in the molecule. The molecule is a very fluid molecule. The molecule can be in constant rotation all the time and constant movement. And this is one of the ways that it begins to move and work out for us. So these constant rotating bonds begin to happen. And we can focus in on some of these single bonds and begin to talk about gauche and begin to talk about anti and begin to talk about eclipsed and staggered. And that's what we basically discussed in our Module 3 toward the very end. Well, what about alkenes? Do alkenes do this? Well, if we take a look at the structure with an alkene, it is a carbon double bonded to a carbon. And here we get two more groups, and there we might get two more groups that get attached to that carbon, so it can have four. But I want to focus on that double bond. And I want to go in and talk about the double bond in a little bit more detail. So here's a sigma bond. This is the initial bond that is formed between those two carbons. And then these two carbons will have empty p orbits. And we said that this gives an overlap, and that creates the double bond characteristic that we see in the alkenes. So the overlap of that p is one bond, and then the initial bond between the two, there's our second. So this is a double bond. Now here's the problem. If we begin to rotate these bonds, just like we did in the alkane world, what will happen is that the p orbits will begin to snap. They don't really overlap that well. And if they don't overlap, then that means there's not strength and there's not additional bonding that begins to happen. And if this is the case, it will actually completely destroy the double bond characteristic. So alkenes do not give us rotation about that bond. That also means that these groups that get attached to those carbons, they become locked in place. Once they go and attach, they could kind of point up, don't they? Look at that. Look at the way that I've drawn that. Or they could slightly point down. Well, if they slightly point up or if they slightly point down and then they cannot rotate on top of that, we could have a bigger problem at hand. And that bigger problem now is what if we have two carbons that have come together for a double bond, and I've got maybe a CH3 here and a CH3 there. Or what if those two carbons came together again, and this time those two CH3s are opposite of each other? In the world of alkanes, this would not be a problem. If this was an alkane, well, what would happen is that this would be a single bond, and this bond could freely rotate around and around and around and around, and we would constantly get both. We would get a version that looks like the one to the left, we would get the version that looks like the one to the right, and this would flip back and forth, back and forth, back and forth, back and forth. That was the whole concept of the Newman projections, and that's kind of what it showed us. The problem, though, is that we are in the world of alkenes, not alkanes. And alkenes, because of the pi overlap that is needed, which is the p orbitals that have to overlap each other to share that space and to share those electrons, we get this double bond characteristic that prevents rotation. That also means that these two structures are regarded as different ones. Oh, now I see where he's going with this. They're different structures. That also means they have different names. The molecule to the left has a different name than the molecule to the right. And it's all based on this concept that double bonds do not twist and turn. Double bonds, when they form, are locked into place. They're locked into place. And the groups that go on these structures are going to be stationary, meaning there is no free rotating bond in order to get them to go back and forth between each other. So we have to be able to designate which one of these are we talking about. You know, sometimes it doesn't matter. I mean, we've not talked about that all the way up until this point. We've done all of those examples. Every single one of those examples in the past, we did them without this thought process. And sometimes that's okay. Sometimes we don't need to know this detail. And therefore, they'll give you the structures like they've given you before, and they just say, name it. Name it, name it, name it, name it, name it. And that's what we've done. But now, they're going to get more particular. Now they're going to highlight the double bond, and they write it in the middle, just like I did here. And then they draw a bond up and down, and then on the right-hand carbon, up and down. And when they set this template up, they want me to be able to go one more step. Name it like usual. But they want me to go one more step, and this is what they want me to do. There is a term that we really have seen before, and this was in Module 3 when we began to talk about the ring structures and the chairs and the axial and the equatorial bonds. And we brought in a term called cis, and we brought in a term called trans. We're going to use those same prefixes here, and this is how we do it. If you look at this particular structure to the left, when we use cis and trans, we look at the hydrogens. Hopefully the left-hand carbon will have a hydrogen on it. It does. It's pointed up. And hopefully the right-hand carbon will have a hydrogen on it. It does as well. It's also pointed up. These groups are on the same side, and they're both pointed up, and because they are the same, we call this the cis form. So I can put the word cis in front of the names that we have been generating all of this time, and this will give you an idea of the shape that these organic molecules are beginning to take. It also gives you an idea of the geometry around the double bond area. All right, the one to the right-hand side, I do the same thing here. There's a hydrogen that points up. Here's a hydrogen that points down. Because these are in opposite directions, we are going to call this one the trans notation. So to the left, we have the cis form, and to the right, we have the trans form. And all of this is because that double bond cannot turn and twist and rotate. They are locked into place at this point. Okay, so now let's do a real example. I kind of done one already. I'm just going to redraw this, and we're going to do a full-blown name of it. And I'll show you the differences. Up until this point, we've been giving things like this. Name it. Okay, well, I'll go through and I'll name it. There's 1, 2, 3, 4 in total. So this is going to be called a butene. And at carbon number 2, we have the double bond. So we called this 2-butene. And I said, good, check mark, move on to the next. That's great. That still holds true. There's no difference in that. And sometimes that's all that we need. However, these problems can go more specific. And what you could see them do is something that looks like this. And they'll say, name it. Well, how do we do that? You do it just like before. You find the longest carbon chain. All right, so the longest carbon chain, right there. That longest carbon chain is still 4. So butene. That double bond still happens at carbon number 2. So it's still 2-butene. But the reason that they took the time to draw it this way is because they want me to take the time to look at the geometry of the molecule that they drew. And here I see a hydrogen that's pointed up, and I see a hydrogen that's pointed down, and they are in opposite directions. So we put the word trans out in front. So it's just an extra little tidbit of information. And I would have never known cis or trans from the way they've drawn this one. That's why we didn't bother with it. I mean, it's not set up in the template that it needs to be set up in. We need to see that double bond in the center, like this, and we need to typically see something pointed up and something pointed down. And when we do that, we can easily assess whether or not this is the cis or trans notation. Otherwise, it's very difficult to do. All right, well, let's see that they give us this, and they give us this, and they give us this, and they give us this. I still treat it the same way. I find the longest carbon chain, and the longest carbon chain, there's 1, there's 2, there's 3, and it just comes down and goes back down. So there's 4. So this is still butene, and it's still happening at carbon number 2. And the hydrogens here are pointed both up. If they both are point down, it's the same thing. They both point in the same direction. And in that same direction, that prefix is going to be called cis. So that is a cis-2-butene. Folks, this is the difference of when it's required and when it's not. Once again, not every problem is going to require it. However, sometimes when they set the problems up the way that they've done it here, they're giving you a clear indication that the geometry is going to be very important. And they want you to provide that cis or the trans in front of those names when that begins to happen. All right, so let's take a look at another example. Let's say that they draw me this structure that looks like this. Ding, 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 ding. Cis or trans is kind of what they want. And then they slap these groups on. Oh. Really doesn't look like the 2 up above, does it? It also really doesn't meet the definition that we talked about either, does it? This carbon has a hydrogen, but there's 2 of them, so which one do I look at? That's weird. And the carbon to the right-hand side, there is no hydrogen there. Which one do I look at there? So this one cannot have a cis or a trans notation. It could have a different notation, but not a cis and a trans one. In order to use cis or trans, you really have to compare hydrogens. That is what this is designated for in the world of alkenes. All right, let's do another example. C double bond C, and we do that. And up here, let's do CH2, CH3. And here, let's do a hydrogen. And then here, let's do a CH3 group. And here, let's do a CH3 group. And it says, give me the cis or trans. Okay, so the carbon to the left, it has a hydrogen. That hydrogen's here. And then the carbon to the right, well, that one doesn't have a hydrogen, does it? Nope, it doesn't. So I cannot compare hydrogens here. So this does not have a cis or a trans form. It's as simple as that. It could have a different terminology that we need to bring into the picture, but because it doesn't have two hydrogens for me to compare, it cannot be labeled as cis or trans. And if that's what the question wants, that's the way that I'm going to have to answer it. It's not possible. A different nomenclature might exist, but not in regards to cis and trans nomenclature. There's no way that it can do that. All right, let's look at another example. Let's say that they give us a skeletal structure that looks like this. And they want me to name it, and they want me to also include cis or trans if possible. Well, take a look at the carbons. Here's the carbon of the double bond, and there's the carbon of the double bond. They have set this up in a way that it is going to be very easy for me to figure out if this is cis or trans or not. But let's do the normal name of it first. We have to start there. If you can't start there, then we can't answer the problem. So we have to provide a name. 1 carbon, 2 carbon, 3 carbon, 4 carbon, and 5 carbon. Okay, so this is a pentene. The double bond is closer to this end, so this is going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So at carbon number 2, I see the double bond. There's really no other groups for me to name. I mean, that longest chain includes everything that's here, but they did tell me to identify if it was cis or trans. Well, they've left something off, and what they've left off is the fourth bond that's here and the fourth bond that's there. Notice if I put the dashed lines in there, it really does set it up just like we've done some of our examples before a couple of seconds ago. But the reason that they've not drawn it is because this is a skeletal structure. And they like to leave off hydrogens in the skeletal structure, don't they? I mean, this was something that we talked about back in the day. So it's understood that the fourth bond that this carbon has, that fourth bond is to a hydrogen. And if this is pointed down, it's automatically assumed that that one goes up. And then over here to the right-hand side, this one's pointed down. So therefore, it's automatically understood that that fourth bond is going to be pointed up, and that goes to a hydrogen. They did not draw it in the skeletal structure because they didn't have to. It was understood to be there. It was understood to be that way. That was all incorporated in module number 1. That's why we talked about it back then. So now we can clearly see if this is cis or trans, because now this hydrogen's pointed up, this hydrogen's pointed up, they both are pointed in the same direction, and because of that, this is going to be the cis form of 2-pentene. And that is how we make that decision. All right, let's look at another skeletal structure. Those always seem to be the one that gets people a little tricky. All right, so here we go. Name it. And then we're going to assign whether this is cis or whether this is trans. Okay, so skeletal structure's there. I need to find my longest carbon chain. My longest carbon chain here, 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, 7 carbon, 7 in total. So this is a heptene. E-N-E. Well, I've got to figure out where the location of the double bond is at. So if I start left-handed, that's 1, 2, 3, 4. If I go right-handed, that's 1, 2, 3. So right-handed is the way to go. So 1 carbon, 2 carbon, 3rd carbon, 4th carbon, 5th carbon, 6th carbon, and 7 carbon. But the question said, and there's no other substituents or groups for me to name, so the question said, is this cis or is this trans? Well, once again, it's a skeletal structure. So on this carbon that's right here, there's a bond that points down. So it's understood that this bond will go up. It's not drawn, and it's understood to be a hydrogen in that location. On this side, the same deal. There's a carbon that's there. This bond is pointed up, so therefore this bond's going to go down, and it's understood to be a hydrogen at that location. So now if I take a look at the geometry of the molecule, I see the hydrogens on opposite sides, and if they're on opposite sides, this means trans. They are across from each other. So this is a trans 3-heptene. So please keep in mind, double bonds do not flip-flop back and forth like single bonds do. And this is the reason that we have to sometimes put cis or trans in front of the names. There is geometry at play. These are different molecules, as you can see, geometry-wise they are. And a lot of times with our biology, things rely on a lock and key model. So think about a key. A key might be made up of the same stuff, just like these molecules are. They're made up of the same stuff. But that key is going to be specific to the lock that's in your door, and that is due to the shape of the key and the shape of the lock, and it has to perfectly fit. And cis or trans changes the shape of the key, and it could not work after that begins to happen. And this is why it's very important, especially in a laboratory facility, if I'm making something like a pharmaceutical drug and giving it to you to take, that drug, we have to study all geometries of it. And we have to make sure that those geometries are safe. Because one could be safe and does what it says it's going to do, while the other could cause cancer. Or the other could be a mutagen. And we don't want that to happen, do we? It happened way back in the day with thalidomide. Pregnant women were taking drugs with geometries that were different. We had no clue that the geometries were going to play such a major role at the time that this was released. And those pregnant women, many of them ended up with deformed babies at birth. And it was simply due to this whole cis and trans and geometry related organic. And now you can kind of see why this is important. Now, in a laboratory, we can switch from one to the other. Now, the molecule can't do this on its own. But we can get this to go from cis to trans and trans to cis. But it requires a little bit of something from us. We have to put the necessary energy in order to get this to break and flip. And in order for that to happen, we have to heat this substance up greater than 180 degrees Celsius. Or we have to provide some type of light energy that would also pack a wallop in order for that to switch and turn around and snap back into place. So I can go from cis and I can go to trans, or trans back to cis, depending on what it is, if I play around with temperature and if I play around with energy. So that's just something, a little nugget of information that I'm putting out there, because this is going to come back a little bit later on. All right. Maybe not in this lecture module, but it will come back in a future module with the class. So cis and trans, we can flip back and forth if we play around with our temperatures. All right. Another reason that cis and trans is pretty important is here. So let's say that you want to go and become an eye doctor, okay? Well, one of the ways that we see is through the molecule of rhodopsin. So here's the structure of rhodopsin. Notice the way that this structure is oriented. This opsin, just think of like a bigger protein, big glob of molecule right there. And then off of this, look at this. We've got a double bond, a single, a double, a single, a double, a single, a double, a single, a double, a single, and then it goes into a ring. I mean, that is the world of organic right there in hand. Look, and all of that you've been learning in this class. Look, see, I know there was a purpose in this, but there's one bond in particular with rhodopsin. And rhodopsin's bond that is very important is going to be this one. They've highlighted it there for you. It's a cis double bond right now. How did they know that it was a cis double bond? Well, think about it. It's skeletal structure. So this carbon has a bond that's pointed down, and there's understood to be a bond that points up. And then on this carbon, there's a bond that points down, and there's a bond that's understood to be pointed up. It's not drawn, but they're understood to be hydrogens, and these hydrogens are on the same side of the molecule, and because they're on the same side, ding, 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 there it is. It is a cis formation at this point. Well, you see, because of the switch that rhodopsin makes. What gets this to turn from cis to trans? Remember, I told you 180 degrees. I don't think that you're going to be putting your eyeballs into a solvent or into a solution that's almost double the boiling point of water. At least I hope not. But light energy was also another alternative, wasn't it? I wrote down HV. And I said, if you have enough energy, the light energy could actually do it as well. Oh, so we see, because light energy could actually target rhodopsin and target this cis bond and turn it into trans. And that's exactly how this process works. So this is a trans bond because I've got a carbon here and I've got a carbon there. And this is pointed down, so this will go slightly up, and that's understood to be a hydrogen. This is pointed up, so this one goes slightly down, and that's understood to be a hydrogen. And these are on opposite sides of the molecule. Opposite sides means trans. Folks, real life organic right here. And this organic reaction happens inside of your eyeballs every day, all day, whether you knew it or not. See how important organic is to you. It makes, hopefully, sense as of right now. All the other pieces of the bonds, all the other pieces of the molecules, who cares about that right now? But this is why cis and trans is so important. It's just one example. Just one example, that's all. Another thing that I want to say before I stop the video is that the trans notation will be more stable. If you look at the way that we have drawn these structures over time so far, that you've been with me, we have constantly done this zigzag thing, right? That is just the way that these bonds really like to be. And cis and trans is no different. There is a preferred method. And the preferred method is actually trans. It gives these molecules, or these parts of the molecules, enough room to move around. It makes the houses in the neighborhood perfectly positioned so they do not overlap as much. So out of these two, trans will be a more preferred way of a molecule to orient itself. And that is why we do the zigzaggy notation almost every single time for an organic molecule. All right, so here's where I'm going to stop. And in the next video, we are going to do this example. So it says, draw the cis and trans isomers, if they're possible, for each of the following, and then name them. So I'm going to have to take these groups, I'm going to have to draw the structures, all the possibilities if they exist, and then I'm going to have to name them, each one. So this is what we're going to do in the next video. So I would say at this point, before you start the next video, attempt these 4 questions. Okay? Go through, answer them, name them just as they're written, and then focus in on the cis, if there is one, and draw it properly, and then focus on the trans, if there is one, and draw it properly. And that's what we'll talk about in the next video when you come back.